Today, we are going to learn about real numbers. Chapter 1, Real Numbers. First, let us know what are real numbers. Real numbers constitute the union of all rational and irrational numbers, both rational numbers and irrational numbers. So, any real number can be plotted on the number line. In this chapter, you will learn about Euclid's division lemma. Euclid's division lemma, it states that given two integers a and b, where a and b are two integers, there exists a unique pair of integers q and r. A unique pair of integers q and r such that a is equals to b into q plus r, where here a and b are given two integers, q is the quotient, r is the remainder. Also, the condition is that r is greater than or equals to 0 and r is also less than b. This Euclid's division lemma is equivalent to r dividend is equals to divisor into quotient plus remainder. Here in this lemma, q is quotient, r is the remainder. Euclid's division algorithm. Here, Euclid's division algorithm is a method used to find the HCF of two numbers a and b. Here, one of the numbers should be greater than the other. We apply Euclid's division lemma here to find out the integers q and r, that is quotient and remainder, such that a is equals to b into q plus r, where r is greater than or equals to 0 and is less than b. If r is equals to 0, HCF will directly be b, or else this Euclid's division lemma, we need to continue. This method is being repeated until we get this remainder as 0. Fundamental theorem of arithmetic. This fundamental theorem of arithmetic, it states that prime factorization for a given number is unique if the arrangement of the prime factors is ignored. If we ignore the arrangement of the prime factorization, then the prime factors are unique. For example, we have taken 36. The prime factorization of 36 is 2 into 2 into 3 into 3, or it can also be written as 2 into 3 into 2 into 3. Here, overall, in the prime factorization of 36, we have 2 2's and 3 3's. 2 3's. Here, 2 2's and 2 3's. Therefore, 36 is represented as the product of prime factors of 2 2's and 2 3's, ignoring the arrangement. In this chapter, we have two methods of finding the HCF. First method is prime factorization, and the second method is using division, Euclid's division algorithm. First, we'll see prime factorization method. Given two numbers, we express both of them as product of their respective prime factors. Then we select the prime factors that are common to both the numbers. This we have done in our lower classes. For example, we'll find out the HCF of 20 and 24. Prime factorization of 20 is 2 into 2 into 5, whereas prime factorization of 24 is 2 into 2 into 2 into 3. Now, what is common among these two, 20 and 24? Prime factorization of 20 and 24, 2 into 2. Here also 2 into 2 is common, the product of which is 4. Therefore, the HCF of 20 and 24 is 4. This is how we find HCF using prime factorization method. Now, we will use Euclid's algorithm to find the HCF. So in Euclid's algorithm, as I have said earlier, it is a repeated use of Euclid's division lemma to find out the HCF. For example, we'll find out the HCF of 18 and 30. We will put 30 as the dividend and 18 as the divisor. Normal division. 18 ones are 18. Difference of 30 and 18 is 12. Here 12 is the remainder which is not 0. So we will again repeat this division taking the divisor as the dividend and the remainder as the divisor. So again normal division, 12 ones are is 12, 18 minus 12 is 6. Again 6 is not equals to 0. The remainder is not equals to 0. So we will repeat the division lemma again. 12 becomes the dividend, 6 becomes the divisor. 6 into 2 is 12. Here 12 minus 12 is 0. Here we got the remainder as 0. So our HCF becomes 6. Here, in this way, we find out the HCF of two numbers using Euclid's division lemma. Till we get the remainder as 0, we need to repeat this Euclid's division lemma. This is how we find out the HCF using Euclid's algorithm. Now, we know this relationship between product of two numbers and their HCF and LCM. We know that product of two numbers is always equals to their HCF and the product of their HCF and LCM. However, this relationship holds good for only two numbers. It doesn't hold good for three or more than three numbers. Revisiting the irrational numbers. Now, the numbers which cannot be expressed in the form of p by q, they are called as irrational numbers where q is not equals to 0. For example, root 2 pi, etc. In this chapter, you get a question where we need to prove the root of some number is irrational. So here we prove this using contradiction method. What do we do in this contradiction method is we assume that the given statement is true and at some point we get a contradiction in our assumption, thereby proving the contrary. For example, let us prove that root 7 is irrational. So our assumption is, let us assume that root 7 is a rational. So as root 7 is a rational, it can be expressed in the form of p by q. That is, root 7 is equals to a by b, where here a and b are co-prime integers. Co-prime integers, remember this now. Now on squaring both the sides, LHS and RHS, we get root 7 whole square is 7 and a by b whole square is a square by b square. Cross multiplying, a square is equals to 7 into b square. With this, we can say that 7 divides a. Then there exists a number c such that a is equals to 7c. Again on squaring, a square is equals to 49c square. So here again, we can say that 7b square is equals to 49c square. Or we can also say that b square is equals to 7c square. Cancel here, 7 ones are 7, 7s are 49. Here it states that 7 divides b. Since 7 is a common factor for both a and b, it contradicts our assumption as we have taken a and b are co-prime integers. As we have taken a and b as co-prime integers. So our assumption was wrong. Hence, root 7 is irrational. This is how we prove using contradiction method. Now, terminating and non-terminating decimals. What are terminating decimals and what are non-terminating decimals? Terminating decimals are the decimals that end at a certain point. It has an end point. I mean, 0 0.2, 2.56, they all stop. But whereas non-terminating decimals, they do not terminate, they don't stop. Example 0.33333, so on. Here there is no end for it. In the same way, 0.1313523, so on. It doesn't end there. These non-terminating decimals, there are two types, recurring and non-recurring. Recurring, it means a part of the decimal repeats indefinitely. Here, just have a look. 0.142857. Again, 142857. The next number, the next part also will be 142857. In this way, this part, that is 142857, will be repeating indefinitely. So this part will be recurring, coming again and again. This is called as recurring. Non-recurring, that is no part of the decimal repeats indefinitely. Fine. For example, our pi 3.1415926535 and so on. You must have noticed that no part is being repeated. So this is called as non-recurring. So how do we check that if a given rational number is terminating or not? Suppose if a and b is a rational number, a by b is a rational number, then its decimal expansion would terminate if both the following conditions are satisfied. The first condition is HCF of A and B should be 1. Its highest common factor should be 1. Only then we can say that the given rational number is terminating. The second condition is B can be expressed as a prime factorization of 2 and 5. B should be equals to 2 power m into 5 power n, where m or n or both can be 0. If the prime factorization of B contains any number other than 2 or 5, then the decimal expansion will be recurring. For example, 1 by 40. 1 by 40 is 0.025. It is terminating, as the HCF of 1 and 40 is 1, and the denominator 40, it can be expressed as 2 power 3 and into 5 power 1. Thank you, children.